Hello. Thank you very much for the introduction. My name is Moray Grieve. I'm head of QA at R3. My presentation today is entitled Testing in the Fast Chain. So those who haven't come across R3 before, R3 is an enterprise blockchain or distributed ledger company with Corda as their flagship product. And today I wanted to give you a quick overview of Corda for those who may not be familiar with it, but also to highlight some of the challenges in testing it. So Corda fundamentally enables distrusting parties such as financial institutions to form and maintain consensus about the existence of shared facts in a decentralized manner. So parties can transact directly with each other in strict privacy using smart contracts. Corda was initially developed as an open source product in 2016, and it was released as an enterprise product in 2018. So what are the key concepts of Corda? And I think it's worth kind of going through these because it kind of helps picture some of the complexities with testing. So the first is states. So states represent shared facts such as financial agreements or fungible assets at some specific point in time. You can think of all shared facts over all parties in a network that are transacting with each other as making up a distributed ledger. States are immutable. To update a state, you must create a new version. Hence, the life cycle over time of a shared fact is represented by a state sequence, and that's quite important. The second key concept is transactions. So transactions are the abstraction that consumes input states and creates output states as part of their life cycle. So consumed input states are historic and they can be thought of as spent in the Bitcoin model. The third is contracts. So contracts govern the evolution of states by allowing relevant parties to check for transaction validity. A transaction is allowed based upon some predefined criteria. They are in effect code that is run over a transaction. And the last is flows. So flows enable complex multi-step, multi-party business interactions between parties to be modeled as an asynchronous state machine. They control the flow of information between parties to reach consensus on a shared fact. But there's a few other sort of things that are worth pointing out around Corda. The first is that it's a platform technology. It's not an application. So developers write applications called Corda apps. They run on the platform. The platform offers all of the features and APIs to write highly scalable distributed blockchain applications. The platform runs on the JVM and it's written in Kotlin. So what does the ledger look like? Well, the ledger is the union of all shared facts across all parties. However, no single party sees the entirety of the ledger. They only see states within transactions that they've been involved in. So here we have like 5 participants in a network of parties transacting with each other. Within the network, there are 9 shared facts or states on the ledger. And we can see here them represented as numbered circles. Of these, we can see that Alice can see 2, Bob can see 4, Carl can see 6, Demi can see 3, Ed can see 4. But no party sees any states in the transaction which didn't include them. So for instance, Carl, Demi, and Ed all see state 3, but Alice and Bob don't. That's fundamental kind of privacy property of Corda. Yes. On to transactions. So we can look a little closer at how a state sequence spans over a transaction. So this is quite a classic kind of representation we've got here. So we have 3 transactions. 2 transactions on the left each have 2 input states and 2 output states. These are shown by the light white boxes within the larger grey box. Each transaction is hashed over its contents, and the hash is used as the identifier for the transaction. States are then referenced by the hash of their transaction and the index in the array of the output states. And output states of one transaction become input states of another via these state references. These are kind of the classic transaction chains of typical blockchain systems. But it's important to note the transactions created initially as proposals to update the ledger. It's only when all parties kind of sign and verify a transaction does it actually get written to the ledger. So the last thing was flows. If you remember, flows enable complex multi-step, multi-party business interactions. In the privacy model of Corda, flows are peer-to-peer communications to enable all relevant parties to transact, to come to consensus around the shared facts. So we can represent this here quite simply, where we have a network of parties, Alice and Bob. Alice creates a new transaction proposal and signs it. She sends a proposal with her signature to Bob. Bob inspects the proposal, verifies it with the contract code, signs it. Bob sends it back to Alice. Alice verifies it with Bob's signature, and the transaction is now an agreement. At no point do the other parties see that transaction, so that's the privacy model of Corda. But this is a very simplified sort of model. In reality, the flow is going to include many more parties, and it will certainly include an additional component called a notary, which is used to check for double spends. But Corda is written such that this kind of asynchronous state flow process survives parties being unavailable on the network. This is a property of eventual consistency, which means that the flow will eventually progress, ensuring that consensus is either agreed or refuted. It's also important to point out that this verification of the transaction proposal requires verification of the entire transaction chain for all states in that proposal. So if we remember, the states have a life cycle over transactions. This means that if a party, or should a party not have either the state transaction or contract code to verify an intermediary transaction, it's got to request it from the other party. So this is sometimes surprising, because what it means is that there's a lot of serialized code going over the wire between nodes on the network in order to download contract code to run over a previous transaction. But before I kind of go on to discussing some of the challenges of testing Corda or DLTs in general, it's worth highlighting that Corda is a network of parties. So a party on the network is represented as a node running a particular version of Corda, and a particular Corda or set of Cordaps. So Corda networks are permissioned. We have an identity manager which controls admission of new nodes to the network. We have a network map which provides a list of all parties available on the network. So it's a phone book of sorts. And we have a notary that tracks states to prevent double spends. And all signed messages and certificates kind of route back to a trust route. This is the basis of trust in the network. So the important point is it is a network, and it's effectively a sort of a collection of interconnected nodes. So what does all of that mean for testing? What are the testing challenges within R3 and within Corda? And this is really sort of where I wanted to sort of highlight some of the kind of the basics. But fundamentally, it's a platform technology. So this means we have to test all of the potential ways a customer might develop Corda apps to run on the platform. We have to build our own libraries of Corda apps in order to exercise the platform fully. It's also highly distributed, so there's complexity in setting up and controlling realist test environments, as well as automation and test verification. Heterogeneous networks and interoperability. So R3 doesn't control parties on a network, or it may not control the network. That can be controlled by by customers. So nodes running on any particular network can have many different versions of Corda, and Corda guarantees interoperability across ranges of versions, which leads to this combinatorial explosion in test matrices, and I'll speak about this more in a minute. It's also highly secure. It's heavily built around cryptography. Ledger integrity and consistency is everything, so we need to test this aspect to the fullest level. There's also an evolutionary life cycle, so states evolve with time, as does the ledger and as does the Corda platform. So we need to ensure a consistent upgrade path for the ledger across all of the platform releases. It's also highly available, so both nodes and notaries are highly available. So there's lots of resiliency testing is required for these types of systems. And there's also an inherent temporal nature to the platform, so even performance testing needs to take that into account. It's not just across the dimensions of a particular transaction, but it's across a temporal dimension of transactions that have changed over time, or states within transactions. So I wanted to come back to one point and just use this as a kind of like an expose about some of the complexities when you have to test sort of networks of interconnected nodes. So Corda has an interoperability guarantee. So Corda Enterprise 4.0 can be used in mixed version networks seamlessly, transacting with nodes running on a minimum platform version of 4. You'll find that statement on our website. But what does this mean for testing? Well, a typical network might contain nodes running a Corda open source 4.0 version, or an Enterprise 4.0 version, or an Enterprise 4.1 version. But Corda supports a node running many different Corda apps at one time, so that each of those could be running multiple applications. But for simplicity, we can say, okay, there's only one Corda app in play here, but there is likely going to be many versions of that Corda app, so node operators can't necessarily synchronize control and upgrades over Corda apps on the network, so Corda has to support that model. So this means we could have a Corda open source 4.0 node running Corda app with across three different versions, or an Enterprise 4.1 node running a Corda app over 2 of those versions. Now, Corda also provides libraries to help developers build Corda apps and it supports interoperability of those libraries. So this means some of these Corda app versions could be using different versions of the tokens SDK or different versions of an accounts SDK. These are reusable libraries. But along with that, it's supported on 4 operating systems, 2 JVMs, 5 hardware security modules, and 5 different databases. So we've got 8 dimensions there to test over. And it's not only testing a node across those dimensions, but it's testing the interoperability of those nodes. So what does that mean for testing? Well, in a network, the number of unique connections in a network is n squared. It's an n squared problem, or it's n times n minus 1 over 2 to be exact. So for a 6-node network, we actually have 15 potential connections. So if I take an example where we have 6 supported Corda versions, 3 across open source, 3 in enterprise, we have 3 token SDK versions, 2 account SDK versions. We have 5 Corda apps we want to use in our test because we want to develop them in a way that exercises functionality within the network. And we'll say, for simplicity, we just have 2 versions across those. And then we've got our 4 operating systems, our 2 JVMs, our 5 HSMs, and our 5 databases. Well, that leads to 14,400 node configurations, or over 100 million connections. And given that we want to test bidirectionally and across 5 different Corda apps, that's over 1 billion test cases. So clearly that's quite a lot. If you were to run these in the happy path case, which often is the first thing you do is testing, so a clean state, bring up 2 nodes, test the interaction, tear them down. It's about a minute to run a test. That's 2,000 years to run. So it gives you an idea of the kind of the complexity of testing sort of interconnected networks. Now, throwing hardware at this won't help because it's an n-squared problem. I mean, we can throw hardware, but I mean, you double the number of machines you automate on, you're only going to half it. So we really need to reduce the number of node configurations. So how do we do that? So we can use this, well, we can achieve this by using sort of covering arrays or n-wise testing approaches. So if you assume that most issues result from the interaction across 2 different dimensions, you can adopt a pairwise test approach to select the node configurations such that all possible combinations of pairs of values across the 8 dimensions occur. So for instance, we'll always have a test with an Azul JVM running on Red Hat Linux or Enterprise 4.1 with the 1.1 tokens SDK. If we take that kind of pairwise testing approach, we can reduce the number of nodes in our configuration to 34, which gives us 561 connections and about 4 days to run a set of clean tests, which is obviously much more manageable, but is it good enough? We've had to make an assumption that issues will commonly arise across pairs of values. So if we want to try and carry on reduce it, we can assume connections between interconnected nodes will only create issues where the interconnection is across two different Corda-related variables. So we can actually reduce the network density in our test by 10%, and we can reduce that cost. But if we do throw hardware at it, we can throw 20 machines in the cloud, and we reduce it to 4 hours, and that's much more manageable. So where does this kind of take us? Well, ultimately this is a happy path test, and this is only the first test that we're going to do. And we have all of the upgrade paths, we have all of the state flow, catching state flow edge cases, we have all of the performance and non-functional testing. So we do need to really continue kind of really trimming down test times so we can get faster test turnaround times, really to move away from the happy path tests and sort of go to a kind of like a dirty sort of nature. So we can bring all 34 nodes up in one go. We can transact concurrently across them, and we can do it through a dirty ledger. And that's the way the world will be moving. But it's an interesting challenge because a dirty ledger builds state throughout the tests. It means that the ledger could vary between runs, and it could be we have non-deterministic nature in the ledger as we run the test. But it's a good approach. But are there any other approaches? Should we weight dimensions with a history for issues? Should we, within our 8 dimensions, should we drop dimensions based on some vendor guarantees? We do really need to test interoperability between HSMs. I don't think we do in this particular case. Or should we sort of search the parameter space to hunt out issues more intelligently using some form of machine learning or AI approach? These are all interesting questions that we have to answer. So that was my 15 minutes. I hope I've given you a little bit of insight into Corda, some of the challenges around its testing, and it's good to be challenged. Thank you for your attention. I'll open the floor for any questions.